Okay, very cool. Nice to meet you.
So, alrighty. I'm just going to introduce myself. So, hi, everybody. Thank you for joining us today. My name is Dr. Joni Rixobi, and I am the director for the Center for Statistical Consulting, as well as the Institute for Clinical and Translational Sciences Biostatistics, Epidemiology, and Research Design Unit. Don't worry, there will not be a quiz whether or not you know those acronyms. But basically, there are two units. One is in the statistics department, one is in the institute called ICTS. And they are two units of biostatisticians, statisticians, and epidemiologists. And our work is on campus. We're consultants, and we work with researchers at all levels. So that is students all the way up to faculty, staff, administration on a variety of research projects. And those include, anything from IRBs to support for grants, data analysis, queries for cohort and database creation. And so we support researchers on campus. I like to describe us as like a holistic group. So we try to support you from the original kind of impetus of designing your study all the way through the final submission of whatever that subject matter is. Many of you, I think, when you signed up, would have seen some information about us. I'll put our links to our websites on the chat. So if you need assistance, we're happy to provide that. Our bird team also does drop-in consulting on Tuesdays. So we want you all to know that we're here to support you and your research endeavors. And so part of the role that we also have on campus is we like to do these types of workshops regularly so we can equip you all with the skill sets you need to do your data analysis, or at the very least, have a good understanding of the underpinning of certain types of methodology so that you understand them and know how to apply them correctly. And so this Stata seminar is part of that. We know that Stata is a very commonly used and in general easy to pick up statistical software. And we have our wonderful Dr. Chuck Huber joining us today. So Chuck actually works for Stata Corp. And he also previously has been a faculty member at a couple of universities. And so he has decades legitimately of experience presenting on a variety of topics with Stata. I've known him since my time when I was at UCLA, which I think some of you heard me talk about. And so he's a great presenter, loves to answer questions, and likes to make the presentations engaging. So we are honored to have him join us once again. And last piece of housekeeping is we're going to be doing a series of 6 of these. So this is the first in the series. We're going to go once a month all the way through June. So please feel free to join us. These are completely free. And you'll also see a couple of emails coming through in the next few weeks around additional offerings that we're going to have as a unit. So again, thank you so much for joining us. And I'm going to turn it over to Chuck.
Okay, thanks, Joni. Okay, let me share my screen. Oh, I'm going to turn off my video too. Okay, can everyone see the slides okay?
Yes.
Okay, so this is the first in a three-part series on causal inference. So today we're going to talk about just the basics of treatment effects and causal inference. Next month, we're going to talk about some more advanced topics, and then and I guess it'll be March by then, we'll come back and talk about causal mediation, which is much more complex. So we're going to start with the basics today. You can download all the materials, the slides, data sets, and do files at this website. So just go to tinyurl.com/teffects. I pasted this link in the chat window, so you should just be able to go there, click it, and you can download a zip file that contains all this material. Okay. So here's what we're
Hey,
going to talk about.
hey
Oh,
Chuck, just not to interrupt you. Sometimes people
sure.
come in late, like me. We don't see the link. Can you repaste the link into the chat?
Absolutely. Hang on just one second. Okay, there it is. So now it's in the chat window. All right. Share this again. Whoops. Wrong thing. Okay. So here's what we're going to be talking about today. I want to start with just the idea of potential outcomes and parameters, and then we're going to walk through 6 very commonly used sort of basic causal inference estimators. And I'm not going to list them all here because we're going to go through each of them one by one. And then we'll wrap up by talking about how do you pick among these. There's 6 of them. How do you know which one to use and when and why? So we'll tackle that at the end. So I do like to start these talks with a cautionary note because I often hear people make comments or see things in discussion rooms and things where people will say, well, I was using regression analysis, but I wanted my results to be causal, so I switched to structural equation modeling or doubly robust estimators, as though somehow switching the uh, the the flavor of software you're using somehow makes it causal. There's nothing in the math or the software that suddenly magically extracts causal relationships from observational data. You still have to have some sort of a reasonable underlying scientific rationale for why the relationship is causal. What the math and the software is doing is it gives you the tools that you need to accurately do that, assuming that you have a reasonable underlying scientific rationale. But you can't just switch from the regress command to the teffects command and magically you're getting causal inference out of observational data. It's not quite that simple. But what I want to do today is show you the tools and some of the explanation of how these things work. Okay. So first up, we need to talk about treatments and outcomes. We're actually talking about a treatment of some sort and we're the effect of that treatment on an outcome. So a treatment could be something like a new drug, and the outcome could be something like blood pressure or cholesterol levels. Treatment could be a surgical procedure, and we're interested in the patient mobility. Treatment could be even something like a job training program, and the outcome could be employment or increased wages. Or it could even be something in the advertising world where you run an ad campaign that's designed to increase the sales of a product. So this is applicable in all kinds of different areas. So let's kind of walk through the rationale of why we need these sorts of tools. So let's think about smoking and low birth weight for a moment. We might be curious to know if the mother smokes while she's pregnant, does that affect the birth weight of the child? In particular, does it lower the birth weight of the child? Is this harmful in some way? Well, in an ideal world, the best way to do this would be to do an experiment. So we would take pregnant mothers and randomly assign some of them to smoke, and randomly assign other mothers to not smoke. And then once they have the babies, we'd weigh the babies and see which, do the babies of the mothers who smoked weigh less than the mothers who did not smoke. Well, obviously, we can't do this. And this is an extreme scenario where we cannot do an experiment. It would be wildly unethical to do this sort of an experiment. But we'd still like to understand the causal relationship between smoking and infant birth weight. And there are lots of things like this where we can't do an actual experiment for some reason. But we'd still like to, we don't just want to understand correlation. We really want to get to causation. So let's say that we have observational data. We're not going to do an experiment. What we have is observational data. So we have data collected on a bunch of mothers. Some of them chose to smoke, and some of them chose not to smoke. And then we could weigh the newborn infants and compare them. But here's the problem with that approach. If we do that, there may be other factors that go along with smoking that could affect the baby's birth weight. And these factors are the mothers are self-selecting into these groups. And so the mothers who choose to smoke may also choose to do other things that aren't so healthy. They may drink alcohol while they're pregnant. They may be eating lots of food that's not very good for them, lots of French fries or fast food and things like that. So smoking may go along with a whole collection of other behaviors that also affect the infant's birth weight. Conversely, the mothers who don't smoke may also engage in other behaviors, such as eating more healthy and abstaining from alcohol. So not smoking may be part of a cluster of behaviors that all put together lead to higher birth weight in their infants. So it's hard to tease apart, is it the effect of smoking or not smoking? Or is it not smoking along with this other constellation of behaviors that's really causing the differences in birth weight? So we need to be able to tease this apart in some fashion. So questions like this can really only be, as I said, answered with observational data. And again, the main problem here is that when people self-select into the treated and untreated groups, that screws up the interpretation. We don't know if the effect is due solely to the treatment or is it influenced by these other confounders. So I'm not going to read all of this stuff to you. There are some assumptions that we're going to make, but mainly that there's overlap, that everyone in the treated group could have been in the untreated group. Anyone in the untreated group could have been in the treated group. It wouldn't really make sense if there was not, if everyone in the data set couldn't have been in either of the groups. Okay. So, terminology. We're going to refer to the idea that what we're going to do an imaginary thought experiment. We're going to say, what if the people who were treated, what if the women who smoked hadn't treated? What would their outcome have been had the mothers who smoked not smoked? And likewise, what if the mothers who didn't smoke had smoked? These are called potential outcomes or counterfactuals. It's the we can't observe both. In an ideal world, we could rewind time and take the mothers who smoked, those exact same mothers, and then rewind time and observe them not smoking. But that's obviously impossible. But we're going to do a little mathematical trick that allows us to sort of do that. And that's what I'm going to show you here shortly. Essentially, it's a missing data problem. So, what we're going to calculate are several quantities. First is called the potential outcome means. And we're going to label those Y1 and Y0 in the population. So Y1 is the outcome assuming that everyone was treated in the population, and Y0 are the means assuming that no one in the population was treated. And then the difference between those is called, and we're going to call those POMs or potential outcome means. And then we can take the difference between those potential outcome means, and we're going to call that the average treatment effect. Okay, so the difference between Y1 and Y0 is the average treatment effect, or ATE. There's a third quantity that people are often interested in, and it's called the average treatment effect on the treated. So we can calculate this difference between Y1 and Y0 only for the people who actually did take the treatment. So that's another quantity that we can calculate, and I'm going to show you how to do that. Again, some of these assumptions are the conditional mean independence. We're assuming that once we've controlled or adjusted for any confounders that we're talking about, that there's independence between the treated and untreated groups, excuse me, between the treatment and the outcome, or possibly. There's this overlap assumption again, where we assume that anyone in the untreated group could have been treated, and anyone in the treated group could have been untreated. And then we're also making the usual independent and identically distributed sampling assumption that we often make with any other kind of statistical method. So enough about sort of jargon. Let's actually walk through an example because I think it helps make a lot more sense. So here's a scatter plot, and I've not labeled the axes or anything. This is very conceptual at this point. So the horizontal axis here is mother's age. The vertical axis is birth weight, the infant's birth weight. And so there's a scatter plot here, and the points, the observations for the mothers who did not smoke are labeled in green with green dots, and for the mothers who did smoke, those are labeled with red dots. Well, one of the first things that we can observe with the scatter plot is that the mothers who smoked tended to be a little bit older, and the mothers who didn't smoke tended to be a little younger. So there is a relationship between mother's age and the treatment. So the self-selection of being a smoker or not smoker seems to be influenced by the mother's age, and we need to account for that in whatever models that we're going to use. Okay. So what we could do is that we can do this little thought experiment where we would say, well, what if the mothers who did smoke, the mothers in red, so what if the red dots, what if those same mothers at the exact same age, what if they just didn't smoke? What would their outcomes have been had those exact same mothers with those exact same covariate patterns? What would their outcomes have been, the birth weights of their infants, had they not smoked? Similarly, for the solid green dots, the non-smoking mothers, what would the outcomes for their infants have been had the non-smoking mothers chosen to smoke? If given the same covariate patterns, the same age, or any other covariates you want to talk about. So, what would their outcomes have been had the non-smokers chosen to smoke? And those are shown here with the hollow green dots. So, what we observe is shown in solid dots. The counterfactuals are shown with the hollow dots. That's the sort of imaginary data with the thought experiment, had they belonged to the other group. What we're going to do is try to actually estimate this. So what we're going to do is we're going to use the observed data for the smokers, and we're going to fit a regression line for the relationship between smoking and mother's age and birth weight. We're going to fit that regression line only for the mothers who smoked. Okay. And then we're going to do the same thing again for the mothers who didn't smoke. We're going to fit a regression line for mother's age, smoking, and not mother's age and birth weight, only for the mothers who did not smoke. Okay, and that's that green line. So we have two regression lines that we're going to calculate. Then we're going to use those two regression lines to estimate the expected value, the expected birth weight for the infant, assuming that all of the mothers smoked and assuming that none of the mothers smoked. Okay. And the difference between those two expected values is going to be their average treatment effect, or ATE. And that's this orange arrow in between. So we're not going to be calculating the difference between what the observed mean in one group and the observed mean in the other group. We're going to calculate the expected value. Oh, here, let's just walk through this and I'll show you the actual calculations. We're going to be using a classic data set from the causal inference literature from Cataneo. This was published in the Journal of Econometrics in 2010, and it's exactly what I'm talking about. It's a study of birth weight, infant birth weight in mothers smoking. So we have B weight is the infant's birth weight in grams. MB smoke is an indicator variable for whether or not the mother chose to smoke. M married is whether or not the mother is married. M age is the mother's age. F age is the father's age. MEDU is the mother's years of education. And then prenatal 1 is an indicator for whether or not the mother had a prenatal visit in the first trimester or not. So this is the data set that we're going to be working with, and you can grab it off the Stata servers by just typing WebUse Cataneo 2. And this is what the raw data looks like. So we have their birth weight measured in grams, MB smoke, and notice some of the mothers are non-smokers, some of the mothers are smokers. And I'm not going to walk through each of these variables, we just described them. But here's what we're going to do. Here are the actual calculations, how we're going to do this. We're going to fit a regression model, like I said before. We're going to type regress. Birth weight is the outcome variable. Mother's age is the confounding variable. And we're going to fit the model if the mother did not smoke. So we're only using the non-smokers to fit this model. And then what we're going to do is we're going to take the coefficients from this model and we're going to generate the expected birth weight. So at the bottom of the slide here, it says generate Y0. I'm going to generate the expected birth weight for everyone in the data set using those coefficients. So we're going to type generate Y0 equals 3,108 grams, that's the intercept, plus 11.36, that's the age coefficient, times the mother's age. And again, we fit the model only on the non-smokers, but we're generating Y0 for everyone in the data set, okay? And then I don't know if it's obvious, but I just switched slides. It looks almost identical because now what we're going to do is we're going to type regress birth weight M age if MB smoke equals 1. So now we're fitting this regression model for only the mothers who chose to smoke. So now we get the coefficients using only the mothers who smoked. And now I'm going to type generate Y1 equals, and I'm going to use the intercept, 3,237, minus 3.95, that's the negative coefficient there for mother's age, multiply that times mother's age, and that gives me the expected birth weight for everyone in the data set, assuming that everyone chose to smoke, okay? Then what I can do is I can estimate the treatment effect, or ATE, I call it TE here. So generate TE is the difference between Y1 and Y0. Okay, so if I look at this now, this is what I've done. I fit those two regression lines and calculated the difference between them. So let's take a look at this for a moment, because this is really the key. This is the sort of intellectual leap that was made in this world to sort of allow us to do this whole potential outcomes framework. So let's start by looking at observation 40 here, the first observation in the list. The observed birth weight was 2,790. That's the actual observed birth weight. And this mother chose not to smoke. She was a non-smoker. But on the right, I have three columns, Y1, Y0, and TE. Y1 is the expected birth weight for this mother's infant, assuming that she did smoke. Y0 is the expected birth weight, assuming that she did not smoke. Now, what's interesting here is these are the expectations. We know we observed the birth weight for this mother not smoking, but we also have calculated the expected birth weight, assuming that she didn't smoke. And that's the key. We're not talking about the observed birth weight anymore. We're using the observations to generate the regression models to then generate these expected birth weights for everyone in the model. So everyone in the model has an expected birth weight assuming they smoked, and everyone has an expected birth weight assuming they did not smoke. Okay. And that's the sort of intellectual leap here that we're making. And so every mother has an expected birth weight under both conditions. Then I can subtract the difference between them for every mother in the data set. And so that difference is going to be the treatment effect. Now what I can do now that I've estimated these things is I can calculate the mean of each of these quantities. So if I estimate the average for Y0, that's 3,409. So that 3,409 means that if, assuming that no one in the population or no one in the sample smoked, the average birth weight would be 3,409. Y1, the average is 3,132. That is assuming that everyone in the population smoked. If everyone in the population smoked, the average birth weight would be 3,132. Okay. And the difference between those, the average treatment effect, or ATE, would be minus 277. And what we're calling this and are interpreting this is that for mothers who smoke, their infants are on average 277 grams lighter than the infants of mothers who did not smoke. Okay. And because of the way we've done this calculation, assuming that we have a biological rationale for this relationship, we can make the leap here that smoking is causing this, okay? Because we've adjusted for mother's age in the model, and we're going to ignore other confounders for now. We're just focusing on the idea here. But we're assuming that we've accounted for any confounding or other things with our model. So we would conclude then that mother's smoking causes the infants to be about 277 grams lighter. Okay. So that's if we were to do this manually, and people did this manually up until Stata 13, I believe. This is a fairly old collection of commands. In Stata 13, we added the teffects RA, which is regression adjustment. And that's what we've done here is something called teffects regression adjustment. And we'll come back to the syntax in a moment, but what that gives us with one command, we don't have to do all of those steps and generate all that stuff. We just type one command, and it estimates these things for us. It estimates the potential outcome mean for the smokers, and it gives us the average treatment effect. Okay? So any questions up to here? I'm going to go through the syntax and how teffects RA works, but conceptually, are there any questions? If you just want to unmute your microphones, I'd be happy to answer any questions. Again, the intellectual leap here is we can't observe the women under both conditions, but what we can do is calculate the expected value under both conditions. And we're basically treating this as a missing data problem. Okay? So the syntax then, the way this works, let's take a look at the dialog box. There's a dialog box for generically called teffects. That's the command. And then there are different estimators. So at the top in the model tab, we're going to select regression adjustment as the estimator. That's the one we just walked through. What we're going to do is select the outcome dependent variable. So we're interested in birth weight. And for now, we're only going to include the outcome independent predictor variable age, mother's age. And then we're going to use a linear model. You could use logit or probit in here. And then at the bottom here, at the bottom of the tab, we're going to select the treatment variable. So this isn't just any old covariate. We're going to specify what is the treatment variable we're interested in. So we need that in order to do these calculations. So that's going to be MB smoke. It's the indicator for whether or not the mother chose to smoke. So that's how we would set this up in the dialog box. In the stat tab, we can ask or tell Stata what we want to calculate. Do we want to estimate the average treatment effect in the population? Estimate the average treatment effect only among the treated, the ATET, or do we want to estimate the potential outcome means? Okay. So if we look at the syntax here at the top, the command then is teffects. The subcommand is RA for regression adjustment. On the left side, we're going to have what I'm going to call the outcome model. And that is the model that contains the outcome variable, B weight, and any covariates that may be predictors of the outcome variable. So in this case, I'm going to include M age as a confounder or predictor of birth weight. And that's the first set of parentheses. That's the outcome model. The second set of parentheses is the predictor model or the treatment model. So in this case, we only have the treatment variable, MB smoke. We're going to make this more elaborate here in a moment. But for now, we're just going to put the treatment variable in the second set of parentheses. And then I'm going to use the option ATE to display the average treatment effect. No log just suppresses the log likelihood history at the top, the iteration history. So that's what that option is for. So then again, when we look at the output, it shows us the ATE or the average treatment effect along with its standard error and a p-value and a confidence interval. And then it does show us the potential outcome mean for the non-smokers. I think I misspoke earlier and said it was for smokers. This is for the potential outcome mean for the non-smokers. I could use the option ATET, and what that's going to do is show me the average treatment effect using only the people who were actually treated in the sample. For conceptual reasons, sometimes people are interested in that number rather than the average treatment effect using the full sample. And again, it shows us the potential outcome mean for the non-smokers. We could also use the PO means option, and what that will do is show us the potential outcome means in each of the groups. I honestly don't know why we don't just display all of these in one set of output. That's never made sense to me, and I don't know why. It's an obvious question. Why do we have to have three different options to display these? Why not just put them all in there? And I don't know the answer to that. Maybe one of these days I'll walk down to the econ group and ask why that's like that. But we have these options, so you can display whatever you want, ATE, ATET, or the potential outcome means, okay? And again, the ATE is just the difference between these two potential outcome means, okay? So that's regression adjustment. That's sort of the most basic version of this potential outcomes idea, okay? So next up is an idea called inverse probability weighting. We're still using this potential outcomes idea, but we're going to use the mathematics is going to change slightly. So again, I have the same sort of graph that I had before. I have mother's age on the horizontal axis, and I have birth weight on the vertical axis. And what I'm going to do, I've represented each of the observations using a hollow circle of different sizes. Those hollow circles are the inverse of the probability weights. What that is the inverse of the probability that the mother belongs to the other group. So the younger mothers, actually, sorry, I misspoke. It's the probability that the mother belongs to the other group. So the younger mothers, notice that older mothers tend to be smokers, younger mothers tend to be non-smokers. So of the mothers who smoked, the red circles, the younger mothers among the smokers are more likely to have been non-smokers. Okay. Similarly, the green circles, the older non-smokers are more likely to have been smokers than the younger mothers. And so what we can do is actually calculate the probability that a mother belongs to the treated group, that a mother self-selected into the treatment group, given the covariates in the model. The reason the circles, I think when I fit this model, it's been years ago that I created this, but I think I included other covariates, and that's why the circles aren't as obvious as you would think they would be. So what we're going to do is use multiple covariates as predictors of the mother's choice to be a smoker or non-smoker. So let's see how this one works. What we're going to do is, yes, question?
Yeah, we had a question in the chat. Someone just wanted a little bit of additional explanation of the difference between ATE and ATET, specifically how you interpret them.
The ATE is the difference between the potential outcome means using everyone in the sample. And the average treatment effect among the treated is the calculation that we calculate the difference between the potential outcome means only for the mothers who chose to smoke. I think the rationale is that often people are interested in that only for the people who smoked because we're curious about the behavior of the people who actually got the treatment. It's more of a conceptual thing than and I don't have a really good explanation as to what those rationales are. I just know that sometimes when researchers are looking at this, there are reasons why they want to focus on just the people who were observed to have the treatment. Because remember, when we calculate the potential outcome means, we calculate those for everyone in the data set. So we assume everyone was treated and assume everyone was not treated. But then we can use those two potential outcome means to calculate the difference. And sometimes there are reasons why people think that should only be calculated. The difference between those should only be calculated for people who actually took the treatment. Um, Sorry, I don't have a better explanation for you than that. But that's how it's calculated. Not a very good explanation. Sorry.
They said thank you, and they said that was great.
Okay. I know the mechanism, but I don't fully understand the reason why people do that. Okay, so back to inverse probability weighting. So what we're going to do, again, the idea of inverse probability weighting is we're interested in predicting the choice of self-selecting into the treatment group or not. So I'm interested in predictors of the choice to belong to the treatment group. So what I'm going to do is I'm going to fit a logistic regression model for smoking. So smoking is now the dependent variable in this model. It's my treatment variable, but for our purposes right now, we're going to use smoking, the treatment variable, as the dependent variable in a logistic regression model. And I'm going to include M age in the as a predictor of smoking. So essentially, I'm asking the question, does mother's age influence the choice to smoke or not smoke? Okay, predictors of the treatment. And once I fit this model, I really don't care about the odds ratios and so forth. All I really want to do is calculate the predicted probability that a mother chooses to smoke. I want to predict that for everyone in the data set. So every mother then gets a predicted probability that they choose to smoke. For the mothers who did smoke, so at the bottom of the slide here, it says generate IPW equals 1 divided by PS if MB smoke equals 1. So what I'm going to do is calculate the inverse probability that the mother smoked only for the mothers who smoked. Okay. For the mothers who didn't smoke, I'm going to replace the inverse probability weight with 1 divided by 1 minus the propensity score, the probability that the mother chose to smoke. Okay. And so what this gives me is an inverse probability weight. It's the inverse. You can kind of think of it as the probability that the mother could have belonged to the other group. Okay. Because the PS, the propensity score, is the propensity that the mother did smoke. Okay. So we're going to calculate these IPWs or inverse probability weights. And then what I'm going to do, oh, here, I've actually got a table in here that shows you this. So person number 40, we have their birth weight. This mother was a non-smoker, but the propensity score, the PS, is 0.16. So the probability that this mother chose to smoke, given her age, is pretty low. It's 0.16. And that makes sense because the mother was younger. Had she been older, if we find a mother who's older in here, it's going to be, well, actually, this is the inverse. I'm sorry. PS is the inverse. No. PS is the probability weight. IPW is the inverse. Anyway, we calculate the probability that the mother had chosen to smoke, calculate the inverse of that. And what we're going to do then is fit the regression model for birth weight and smoking. Okay, so at the top I have regress. Birth weight is the infant birth weight. MB smoke is the treatment variable, smoking and not smoking. And what we're going to do is we're going to weight each observation by its inverse probability weight. So in these square brackets, it says A weight equals IPW. And when I run this regression model, it gives me a coefficient for MB smoke. That coefficient is the average treatment effect. Okay. So that is the underlying mechanism of how we calculate inverse probability weighting. It's much easier to do this with the teffects IPW command. So here at the bottom, we have teffects IPW. Actually, let's walk through the dialog because it makes it a little easier. So I'm going to go to the teffects dialog box again, and this time I'm going to select the estimator inverse probability weighting. Now I'm going to have just an outcome variable. There's no outcome model. There are no predictors of the outcome variable here. But I do have the treatment dependent variable. So now I have a treatment model. So the treatment dependent variable is smoking, and the predictors of treatment is M age, mother's age. So now I'm looking at predictors of the treatment, and I can then select the treatment model. I could use Logit or Probit. So if I fit this, let's talk about the syntax first. The syntax is tffx IPW. The first set of parentheses are the outcome model. Now, in this case, it's just the outcome variable, but here shortly, that's going to be an outcome model again. Now, the second set of parentheses is the treatment model. Okay, and before it was just the treatment variable, but now we have an actual treatment model. MB smoke is the treatment variable, but it's the dependent variable in this treatment model. M age is what we think is a predictor of the treatment. And then we can type comma probit. I'm going to use probit instead of logit this time to fit the treatment model. And then I've used the option PO means to see the potential outcome means in each of the groups. Okay. So when I do this, it fits the model and it gives me the potential outcome means in each of the groups. Okay. So it's just a different way of using this counterfactual idea to estimate the potential outcome means. And if I change the option to ATE, it shows me the average treatment effect as well as the potential outcome mean in the non-smoking group again. Or I could do ATET and it does the same thing, but it does this only, it estimates the average treatment effect only for the treated people who were actually treated. Okay, so that's inverse probability weighting. It's just another mathematical way of estimating treatment effects using this potential outcomes strategy. So any questions about inverse probability weighting? Notice that the results are very, very similar. They didn't change much.
I have a question. Can you add multiple treatment predictors in that treatment model in the parentheses for like MB smoke? If you have M age, could you add other variables there as predictors?
Oh, absolutely.
Okay.
And in real life, you almost certainly would. I'm just trying to keep this as simple as possible so we can focus on sort of the method. But in real life, yes, you would want to put lots of whatever you think are predictors of the choice to smoke. Could put that in there. Yes.
Can you talk a little bit about why you would choose to do this instead of the previous one? It seems like the previous one requires more assumptions about the data
Yes. So we'll talk about
and
this
the
more at
independence
the end.
between. Okay.
Yeah, we'll talk about this a little more at the end as to choosing estimators, but I think the rationale generally for choosing IPW, inverse probability weighting, is if you think here we're focusing on what do we believe are predictors of the choice to have the treatment. So we really are kind of saying, I don't know much about predictors of the outcome, but I think I know some things about the things that predict the choice to be in the treated group or the untreated group. Whereas with regression adjustment, it's the opposite. We were focusing on any confounders that influence the outcome, and we just put the treatment variable in by itself. So the rationale would be, well, if I'm more interested in predicting the choice to be in the treated group, I'd use IPW. If I really don't have much information about that, but I think I know about confounders for the outcome variable, then I would use regression adjustment. Does that make sense?
Yeah, yeah. I guess the other
Okay.
question I had is, so suppose you choose this estimator.
Yes.
Does Are there guidelines for like the quality of the logistic regression predictions for this to be like
Valid.
trustworthy?
Right. It would be like any other regression model. And as I'll show you here in a moment, you can view the underlying model. By default, we just show you the average treatment effect and the potential outcome means. But there is an option that will show you the underlying auxiliary equations, the models that are being fit in the background in order to do these calculations. You can actually display those. And so you probably do want to take a look at the quality of those models, as you say. You might even want to fit them on their own just to take a look and see, do these models make sense? So in this case, I could use teffects IPW, but I might want to go off on the side and fit that MB smoke and MH model separately and just take a look at it and see, does this model make any sense at all? Or am I just throwing variables in here that don't really make sense? So yes, you
Thank
would
you.
definitely want to make sure that the models make sense. Yeah,
Thank you.
sure. Okay. So next up, we're going to see how these two actually come together. And this is called inverse probability weighted regression adjustment, or IPWRA. And what we're going to do here is we're going to put these two together. And they're often called the doubly robust estimators. There are two of these. And that's because essentially, if either one of the models, if the treatment model or the outcome model, if either one of those models is correctly specified, then we should get consistent or asymptotically unbiased results. Um, Before, with either of the others, one of the assumptions is that those models are correctly specified. Because if they're not, we can't really trust the results. Now, the problem in real life is we never really know if our model is correctly specified or not. We can make an argument that it is, but you never really know. There's no statistical test for that. But the nice thing with IPWRA, or these doubly robust estimators, is we're going to use both regression adjustment and IPW together. And so as long as one of those two models is correctly specified, we should get consistent results, or asymptotically unbiased results. And I really like the dialog box for this because I think it helps to explain what we're doing with this estimator. So at the top of the dialog box, here I've selected inverse probability weighted regression adjustment, or IPWRA. So what we have now is an outcome dependent variable, which is birth weight, and I've included multiple predictors of the outcome variable. So I have an outcome regression model, and the predictors of the outcome are things like mother's age, prenatal visit, whether the mother's married or not, and whether it's the F baby, I think is first baby. So that's going to be a linear model for the outcome. So I have a collection of predictors for the outcome dependent variable. But then I also have a treatment model. And this allows me to include covariates that I think are predictors of the self-selection into the treatment group. So what I'm doing here, the treatment dependent variable is MB smoke. That's the treatment variable we're interested in. But I can include covariates that I think are predictors of the mother's choice to smoke or not smoke. And that includes married, so that's an indicator for whether the mother is married. MH is mother's age. F baby is first baby. Med, I think. There are actually other variables in this data set that I should have listed earlier. Anyway, and so then I can choose the treatment model. So you could use logit or probit here. So what I'm going to be doing is both of these things that I just showed you simultaneously, both regression adjustment along with the inverse probability weighting. So now if I look at the syntax at the top, I really should put just the syntax so it's easier to read. But the syntax is now teffects IPWRA. And now I've made this command a lot bigger. So the first set of parentheses now is the outcome model. So birth weight is the outcome variable. And then I have that collection of covariates that are predictors of the outcome variable. And then the triple slash means this command continues on the next line. So on the next line, I have another set of parentheses, and that has MB, and that second set of parentheses contains the treatment model. So MB smoke is the treatment variable, but it's the dependent variable in the treatment model. And then I have a collection of predictors of the treatment. Comma probit says use a probit model rather than logit. And then I want to see the PO means, which is the potential outcome means. And then I mentioned just now that you can view the underlying equations, the auxiliary equations. So you type A equations, the option A equations, and that will show you the models that are used to generate these PO means. So now if we look at the top of the output, we have the potential outcome mean for the non-smokers, the potential outcome mean for the smokers, and below that, we have all these auxiliary coefficients. So what do these things mean then? So now what we have is the outcome model, assuming that no one smoked. Okay, so that's the outcome model. We have the OME1, that's the outcome model, assuming that everyone's, or excuse me, I'm sorry, I said that wrong. OME0, that's the model using only the people who did not smoke. That's that regression model where that we fit only for the people, the mothers who did not smoke. OME1 is the model that was fit only using the mothers who did smoke. And then TME1 at the bottom, that's the treatment model that's that probit model where we're getting the propensity scores, or that before we used logit, now we're using probit instead. But those are the coefficients from those models. Sometimes people like to look at those, but we have to use the A equations option to view those. We could view the average treatment effect. So now I've used the ATE option. So the average treatment effect using the IPWRA estimator is minus 231. So we would say that mothers who chose to smoke on average have infants who are on average 231.8 grams lighter than mothers who did not smoke. Okay. So that in IPWRA is in some ways the ideal if you have information or predictors about both the outcome variable and predictors of the treatment. Okay, that's this doubly robust estimator. Augmented inverse probability weighting, that's another one of these doubly robust estimators, and I'm not going to walk through the math because it's just a variant of IPW. But it also allows you to fit both an outcome model and a treatment model. So this is another doubly robust estimator. And again, it has this advantage of allowing predictors of both the outcome and predictors of the treatment. So we can get those again, potential outcome means, average treatment effect, or average treatment effect among the treated. So those are sort of the basic ones. They're very commonly used. And again, ideally, IPWRA or AIPW, the doubly robust estimators, are best. They're best if you have information on both. Okay. Now, the last two estimators are both based on matching, and there are two flavors. One is called nearest neighbor matching, and the other is called propensity score matching. Nearest neighbor matching is exactly what you would imagine. What we're going to do is imagine if we could have the exact same mother. Again, the idea here is, what if we could take a mother who smoked, observe her, and then rewind time and observe that same mother under the other treatment condition where she didn't smoke? Well, we can't do that, but a good imaginary proxy for that idea is to find a mother who didn't smoke, find a mother who is as similar as her as possible who did smoke. Okay. So what we're going to do is take the covariates that we have in our data set and find a mother who smoked, start with a mother who smoked, and find a mother who is as similar to her as possible among the covariates, match her, and then compare them. So for this first two observations in the far left of the graph, these two mothers are the same age. So one of the mothers smoked, they're the same age, one of them smoked, one of them didn't smoke. So let's say that these mothers are as similar as possible. So comparing them gives us a pretty good comparison that accounts for any confounders in the data set or in the model. Okay. So we can do that for every observation in the data set. For every observation, we want to find a matching mother. Okay. So it's called nearest neighbor matching. If we go to the dialog box, now we're going to select nearest neighbor matching, and we're going to select the outcome variable birth weight, and then select the outcome independent variables. Then we need to select the matching variables. We obviously select the treatment variable. Now, Continuous variable indicator variables are pretty easy to match. So find a married mother who didn't smoke and match her with a married mother who did not smoke. That's pretty easy. But when you start matching on things like age, finding a married smoker who's 36 years old with a married non-smoker who's also 36 years old, that starts to become pretty challenging to find in the data set, especially if you have a fairly small data set. When you do this with multiple continuous variables, not only does it become fairly difficult just to find a match, but it also can introduce a certain bias, mathematical bias. We're not going to go into the math of that, but there is a correction for that bias. And so what you can do is include those continuous variables here at the bottom to correct for large sample bias using multiple continuous variables. You can also, at the bottom of the dialog box, specify exact matching variables, variables that must match exactly. For the continuous variables, what it will actually do is kind of imagine calipers and say, well, I've got a 36-year-old smoker and I don't have a 36-year-old non-smoker to match, but maybe 37's close enough. Or maybe I have to go all the way out to 38 or 35. And so what it will do is sort of expand the calipers to allow matching for continuous variables. You can avoid that by putting any variables in the exact matching box at the bottom. I don't recommend doing that with continuous variables because it will just lock things up. But for indicator variables, often you want to match them exactly for whether they're married, for instance, or whether they had prenatal visits in the first trimester. Okay, so we can fill in the dialog box. That then gives us the syntax teffects NN match for nearest neighbor matching. The syntax is the same. We're going to have the treatment model first with any treatment predictors. Outcome model with outcome predictors. Second set of parentheses is the treatment variable. E-match is the exact matching, and then bias adjust is the continuous variables that we want to adjust for when we have multiple, usually 3 or more continuous variables. And again, we get the average treatment effect here in the output. Okay. Now, that's nearest neighbor matching. That is fairly rarely used because of the problems of matching on that many covariates. What's actually much more common is propensity score matching. How are we doing on time? So propensity score matching avoids this matching on multiple covariates by using logistic regression to take a bunch of covariates and collapse it down into a single propensity score, much like what we did with inverse probability weighting. So what I'm going to do is fit a logistic regression model for treatment, and I'm going to include covariates that I think are predictors of the treatment. So these are predictors of the choice to smoke or not. And just like with IPW, I'm going to predict the probability that the mother chose to be a smoker. And here I'm going to name that propensity score. So I've collapsed 1, 2, 3, 4, 5. 5 covariates or 5 confounders. I've collapsed those 5 into a single propensity score. And then what I can do is I can match based on those propensity scores. So I can find a mother who smokes and find a non-smoking mother who has a very similar propensity score, match them on that, and then calculate the difference in their birth weights. Okay, so this is called propensity score matching. Again, if we go to the dialog box, we would now select propensity score matching. There's only the outcome variable. There's no outcome model. We then specify the treatment dependent variable, the treatment model, and away we go. Okay, so the syntax is very similar to what we had before, and this allows us to estimate the average treatment effect. We're just about out of time, so I'm going to speed up here a little bit. One of the assumptions we have to be able to make, it's critical for propensity score matching, is that mothers with different covariate patterns could have been non-smokers. And so there's a post-estimation command called teffects overlap. And what this does is it checks to see, okay, given the covariates in the model, is it actually possible that those mothers who were smokers could have been non-smokers and vice versa? Because there may be certain covariate patterns where, given that covariate pattern, no one actually smoked or no one actually did not smoke. And so you can type teffects overlap and see the overlap. What we want to see is overlap of these two lines. Okay. So here we have good
Excuse me,
overlap.
Chuck. I'm sorry,
Yes.
we have a hand raised. Ariana?
Oh,
Yeah,
okay.
I'm sorry. I forgot to ask this earlier. It's a really quick question.
Okay,
And
sure.
maybe it's somewhat of a silly question, so I apologize in advance. But can these tfx commands be used with the survey package in Stata?
No.
Okay, so separate.
I don't believe so.
Okay.
I teach our survey course, and I think this is one rare exception where that does not work with the survey weights.
Okay, great. Thank you.
I'll check at the end in case that's changed, because it may have changed. These commands have been around since Stata 13, and when they first came out, I know they didn't. But I'll check at the end before we log off and just double check that.
Okay, thank you.
Sure. Because it may have changed over the last 5 releases or however many, but I don't believe so, no. The good news is if you wanted to do something like IPWRA or even the doubly robust estimators, if you really, really want to do it, I've walked you through in the slides how to do it manually, and you could do all of that with survey weights. So in theory, you could do these things manually. They just don't work with the teffects commands. So yeah. Okay. So lastly, how do we select an estimator? So here I've collected a table of the estimates from each of the models. So teffects RA, the AT is minus 277. teffects IPW, it's minus 275. The smallest estimate is the nearest neighbor matching, that's minus 210. So it looks like we have estimates of the average treatment effect anywhere from minus 210 to minus 277. There are different ways of estimating the effect, and they're going to vary some, and the question then becomes obviously which one do we choose? Nearest neighbor matching is rarely a good choice simply because it's difficult to match on more than a couple of variables. Propensity score matching has become very popular, especially, I believe, in the biostatistics world. And so you often see that one used. IPWRA is really popular simply because of its doubly robust property. So in terms of use out in the wild, I would say IPWRA and propensity score matching are probably the two most popular. And they differ very, very little. Minus 229 versus minus 231. They're going to give you very similar results. But in terms of rules of thumb, I sat down with our director of econometrics years ago when I put this talk together and asked for some rules of thumb, because this is a little outside of my area. The main thing is, and we talked about this earlier, is if you think you know the determinants of the outcome, then use regression adjustment. That would be the best option. If you're pretty sure about the determinants of treatment status, then IPW is going to be a better estimator, because that's what you're predicting is predicting the determinants of treatment. If you're not sure or you have predictors of both the outcome and the treatment, then use AIPW or IPWRA. And again, I think out in the wild, IPWRA or these doubly robust estimators are very popular. If you have a lot of continuous covariates, nearest neighbor matching is just not going to work. It just has too many problems. Just matching is difficult, and then there are bias issues you have to deal with. So that's why propensity score matching seems to have taken the lead by far as the most popular matching estimator. So the ones I would focus on if I were doing this in the real world would be IPWRA or propensity score matching. Depending on what you want to use. The IPW estimators are not reliable if the estimated treatment probabilities are really close to 0 or really close to 1. So generally avoid them there. But I know we're out of time, so I need to wrap up, but I just want to remind you one more time that there's just nothing in the math or the software that magically extracts these causal relationships. You still have to have some underlying scientific rationale. So I can't just throw in shoe size and say, oh, I think shoe size is causal for birth weight of infants. You could do that with the software. You could put something in like large shoes versus small shoes, and it would give you an estimate of the average treatment effect, but that doesn't make any sense from a scientific point of view. Okay. If you'd like to learn more about this, there are some references here, then clickable links to some blog posts And I'm going to go ahead and wrap up since we're out of time. I'll hang around and answer questions as long as you like, but if you think of questions later on, shoot me an email at chuber@stata.com. And again, you can download the slides, data sets, and do files for all of this at this URL, and I already copied it into the chat window. Okay, so I'm going to stop talking. Does anyone have it? Thanks again for being here, by the way, and I'm happy to hang out and answer questions.
Hi, I have a question, which is it possible to send the do files, the codes you used, so that we can run with our data set and understand better?
Yes, that's what is here. I'll paste it into the chat window again. So I just in the chat window pasted a link to a tiny URL / teffects, and if you go to that website, it has a zip file. Just download that, and it has the do file, the with all the code. And it has the example data set and the slides, so everything is in there.
Hi, I have
Hi.
one question.
Okay.
Yeah, so maybe it's kind of basic, but if in case sometimes we have like I work with environmental exposures, so sometimes we have continuous exposures. So do you think that we every time we need to do it binary or categorical to do causal inference?
The short answer is no. Here, these are the basic estimators. What we will talk about next month, you can do either binary treatments or ordinal treatments. What we'll talk about in March will allow continuous or categorical or continuous treatments for things
Okay.
like causal mediation. So these are the basic estimators,
Mm-hmm.
but we're going to do much more sophisticated stuff here shortly.
Yeah,
So yeah,
thank you.
yes.
You may have covered this already, so I apologize. Could you differentiate again the difference between the augmented IPRW versus the non-augmented one? What differentiates those?
So the regression adjustment IPW is just literally a mix of the previous two. So it's literally doing the regression adjustment using the IPW weights. So it calculates the weights and then it uses those weights in the regression adjustment estimator. So it's a literal combination of regression adjustment and IPW. The AIPW, it's been so long since I wrote this talk. It's probably 10 years old now. I don't remember what the mathematical adjustment is, but I do remember the AIPW is just some sort of a mathematical adjustment going on in the background. I don't remember the mechanism or the math that's being used, but it's a little different than the regression adjust. It's still doing IPW, but it's doing something a little different than regression adjustment with it. It's just some sort of it's called augmented. It's a mathematical adjustment that it uses rather than the regression adjustment. And I just don't remember the math behind it. I just remember that it substitutes, instead of using regression adjustment, it uses just some sort of a mathematical adjustment.
Okay, thank you. And is there one that you recommend over the other?
I don't, again, I'm not really a true expert in this world, in this field, but the one I see most often used is IPWRA. And I think because it's easy to understand what's going on, because regression adjustment is fairly easy to understand, and IPW is fairly easy to understand. And so putting them together, they have this doubly robust property. And so I think it's probably the most popular of the non-matching estimators. And then with the matching estimators, propensity score matching is the most popular.
Thank you.
Sure. The information about AIPW is in the methods and formulas in the manual. So if you want to learn more about it, the math is in the manuals. It's been so long. This is an old talk because these are old commands in Stata that have been around since 13, and I just haven't looked at the manual in a while. That reminds me, I promised someone I was going to check to see if you can use survey weights with the treatment effects. Give me just a second. Let's see. Weights, is he robust? No, Short answer is no, you can't.
Thank
So you
you for
can't.
checking.
Yeah, if you ever want to check that, look at the dialog box and go to the here. Let me share this screen. I'll open Stata again. I'll show you how to check that. The way I check it anyway is I go into Stata. Here's Stata. Oh, here it is. And I type db in the name of the command. That opens the dialog box. So db teffects. And that will open the dialog box. If you go under SE Robust, if you click on that tab, if it works with survey weights, it'll have a little box up here that says click to set survey weights or whatever.
Got it.
And
Thank
that'll
you.
be in the SE tab. Like if you do that with regress, if I type db regress and I click on SE Robust, see it says survey data
Mhm.
estimation.
Yeah.
And if I check that box, oh, they moved it down here from up here, but it says survey settings. So I can click on that and go set up the survey settings.
Oh,
So-
okay. Thank you.
So if you just check the SE Robust tab for whatever command you're interested in, just click the SE Robust tab and look for that survey data estimation checkbox. And that's how you'll know. There are other ways to check, but to me, that's the quickest. So,
Cool. Thank you.
sure.
Any additional questions for Chuck? All right. Seeing
Okay.
none. Oh, somebody have a question? Nope. Oh, just lots of thank yous. Okay. All right.
Okay. Well, thanks
Thank
for
you so
being
much,
here.
Chuck.
See you next month.
Yes, sir. Enjoy the rest of your week and your trips. Please travel safe.
Yeah. Yes. Off to Australia tomorrow. So
All right.
17.5 hours on a plane. Yay.
Well, I hope you got a good book.
Yeah. I hope I can sleep. So, all right. See you later.
All right.
Bye. Bye.
Bye.